Hi all. Today we are going to discuss a very important topic, and that is mathematical modeling of mechanical systems. Normally in mathematical modeling we will be asked to find the transfer function of a given mechanical system. So before going into the problem, we should know what is a transfer function, right? So in a simple sense, we can define transfer function as the ratio of Laplace transform of the output to the Laplace transform of the input. So transfer function is equal to Laplace transform of the output divided by Laplace transform of the input. But there we have to apply one condition, and the condition is that all the initial conditions should be set to 0. So all the initial conditions are considered to be 0. So we can define transfer function as the ratio of Laplace transform of the output to the Laplace transform of the input with all initial conditions set to 0. Okay. Or else we can also define transfer function as the Laplace transform of the impulse response with all the initial conditions set to 0. So normally this transfer function is defined for only LTI systems. LTI means it's a linear time invariant systems, right? Okay. So g of s, let g of s be the transfer function. So g of s is equal to L of g of t, where g of t is the impulse response. Okay. So g of s is equal to Laplace transform of a impulse response. Or else, as I told, it can be defined as a ratio of Laplace transform of the output to the Laplace transform of the input with 0 initial conditions. If y is the output, then Laplace transform of output is y of s. And if u is the input, then Laplace transform of u is u of s. So the final transfer function g of s is equal to this y of s divided by u of s with 0 initial conditions. So here we consider the initial conditions to be 0. Okay. So what are the properties of transfer function? So first important property is that the transfer function is defined only for LTI systems. Okay. So linear time invariant systems. Then another property is one of its definitions itself. It is defined as the Laplace transform of the impulse response, right? And third property is that all initial conditions of the system are set to 0. So if you know the proper definition of transfer function, you can easily write the two properties. One is that transfer function is defined as the Laplace transform of the impulse response, right? Then another property is the 0 initial conditions. So all the initial conditions of the system are set to 0. So from the definition itself, you can write the two properties, and the first one is a very important property of transfer function. So it is defined only for a linear time invariant systems. So these three properties are very easy to remember, right? Then fourth property is that the transfer function is independent of the input of the system. The transfer function is independent of the input of the system. So why do we say like that? Because if the input changes, the output will also change. And transfer function means we are taking the ratio of output to input, right? So that will be a constant. Actually, transfer function will be a constant, so it does not depend on the input, right? Then fifth property is that for a continuous system, the transfer function is expressed as a function of s, and for a discrete system it will be a function of z, right? Okay, fine. Now we are moving on to the mathematical modeling of mechanical systems. So mechanical systems means we have to study translational system as well as rotational system. Translational system means a system in which the movement will be like a linear one or linear movement, whereas a rotational system means the motion or the movement will be a rotational one. Okay, right. So firstly we'll discuss a mechanical translational system and how to find the transfer function. So mainly there will be three basic elements associated with the mechanical translational system, and the three basic elements are mass, dashport and spring. So what are the three basic elements? Mass, dashport and spring. Okay. Mass actually represents the weight of the mechanical system. Okay. Mass represents the weight of the mechanical system. Dashport represents the frictional element. Okay, dashport represents the frictional element in the mechanical system, and spring represents the elastic deformation of the system. So the three basic elements are mass, dashport and spring. Mass represents the weight of the system. Dashport represents the frictional element or friction existing in the system, and spring represents the elastic deformation of the system. So you have to remember these three important elements. Okay, and while calculating the transfer function, we have to remember, or we have to understand two main laws that govern the system. So we are going to calculate the transfer function based on these two main laws, and the two main laws that govern the mechanical system are Newton's second law of motion, which states that force F is equal to mass into acceleration, F equal to ma. And the second important principle or law is that it's known as D'Alembert's principle, which states that the sum of applied force is equal to the sum of opposing forces. Or in another sense, we can say that the total force acting on a body is zero. The total force acting on a body is zero. So the total force in the sense, when we apply a force on a mass, so that is the applied force. So there will be, or there is an applied force, but at the same time there will be a force opposing this applied force. For example, if I am having an object with the mass m, so I am trying to move that particular object. For that I need to apply a force, say F. So F is the applied force. I am applying a force F on the mass m. So applied force is F. But when I try to move this particular object, when I apply this force F and try to move this particular object, definitely there will be an opposing force from the mass, and that mass itself will try to oppose the moment. So there will be an opposing force due to the mass m itself, right? So the total force acting on a body will be zero, or I can equate, say, applied force to the sum of the opposing forces. Okay, so that principle or that law is important in our system. Okay, so Newton's second law of motion, which states that F is equal to mass into acceleration, force F equal to ma. And the second principle or law is the D'Alembert's principle, which states that the sum of applied forces is equal to the sum of opposing forces, or the total force acting on a body is zero. Okay. For doing the problems, we should know the force balance equations of these three elements. So which are the three elements? Mass, dashport and spring. So we need to know the force balance equations of these three elements, then only we can calculate the transfer function. Okay, so firstly we will go for the mass element. So here we have the mass element with mass m, and there is an applied force F on one side, and the other side of the mass element is fixed. So that is a reference. So that end is fixed, and on the other end we are applying a force. So due to the applied force F, the mass will move to a particular distance, and the displacement of that mass is x. So it's marked over here, x is the displacement. Okay, so in this case, if we are applying this force F to the mass, definitely there will be an opposing force due to the mass m itself. Okay, so that opposing force due to the mass m itself is represented by F suffix small letter m. Okay, so we will represent the mass with a capital M, but the opposing force due to the mass will be represented as F suffix small letter m, and this opposing force Fm will be directly proportional to acceleration. But here in this case, instead of acceleration A, we are representing that acceleration in terms of a displacement x. So how acceleration and displacement are related? Actually, acceleration is the second derivative of a displacement. So acceleration A is equal to d square x by dt square. Okay, so we will be representing acceleration, velocity, etc. in terms of displacement only. So the opposing force due to the mass m itself, which is represented as F which indicates the force, so F suffix m, where m indicates small letter m, so that indicates the mass, the force due to the mass. So Fm will be directly proportional to acceleration, which is d square x by dt square. So now we are going to remove the proportionality constant by replacing it with another constant, which is m. So Fm is equal to mass m into d square x by dt square. So this is actually Newton's second law of motion. Force is equal to mass into acceleration. Okay. And now by D'Alembert's principle, it states that the total force acting on a body is 0, or the sum of applied force is equal to opposing forces. So in this case of a mass element, so what is the applied force? The applied force is F. And what is the opposing force? The opposing force is due to the mass itself, which is Fm. So now we can equate those two forces. F is applied force. Applied force is equal to Fm is the opposing force. Okay, which is equal to m into d square x by dt square. So here sum of applied force means here we have only one applied force, and that is F itself. So we have only F term. So F is equal to sum of applied force is F, that is equal to sum of opposing forces. Here in this case we have only one opposing force, and that is the opposing force due to the mass itself, which is F. So F equal to F, and that can be equated to, so what is Fm? It is m into d square x by dt square. So m into d square x by dt square. Okay. Similarly, we have the second element, dashpot, which represents the frictional element in the system. So this is the symbol for dashpot. It's like a piston. Okay, this is the symbol, and this B indicates the frictional coefficient. So capital B. Capital B is the frictional coefficient. So it's important. Okay. So here this is the dashpot we have, and the one end of the dashboard is fixed, that is the reference part, it's fixed, and on the other end we are applying a force F. And here also, due to the applied force, this dashboard will tend to move a distance of say x. So that distance is marked over here. So here also let F be the applied force, and due to the applied force, definitely there will be an opposing force also existing over here. Okay, and that opposing force is due to the friction. Okay, so that opposing force due to the friction is represented as F suffix small b. Small b. So Fb, which is the opposing force due to the friction, is directly proportional to dx by dt. So remember, in case of mass, the opposing force Fm was directly proportional to d square x by dt square, which was the acceleration. But in case of the frictional element, or in case of the dashboard, the opposing force F suffix b is directly proportional to the velocity, which is dx by dt. So here also we are going to replace the proportionality constant with another constant, which is the frictional coefficient. So Fb is equal to capital B into dx by dt, where b is the frictional coefficient. So here also, by applying the D'Alembert's principle, we have the total force acting on a body is 0, or the sum of applied force is equal to sum of opposing forces. So we can equate F to Fb. F is the total applied force over here, and Fb is the total opposing force. So F is equal to Fb, which is equal to b into dx by dt. And this is another case in the dashboard system. So if you look here, you can see like the two ends of the dashboard are free to move. So in the previous case, one end was fixed, but here in this case the two ends of the dashboard are free. So no end is fixed, and we are applying a force F over here. As a result, there will be a displacement of x1 say here, and there will be a displacement of x2 for this particular end. So there are two displacements applicable to the dashboard here. Okay, so in this case we can write the opposing force Fb directly proportional to d by dt of x1 minus x2. So in the previous case there was only one displacement, so we wrote Fb directly proportional to d by dt of x. But here, since two displacements are there, we can write the opposing force Fb directly proportional to d by dt of x1 minus x2. So while doing problems, I will make you understand which displacement to be written first. So that we'll see later. Okay. So Fb, replacing the proportionality constant with the frictional coefficient b. Fb equal to b into d by dt of x1 minus x2. So these expressions are very important because we need all these while doing problems. Then this is the D'Alembert's principle, which states that the total force acting on a body is 0, or sum of applied force is equal to sum of opposing forces. Moving on to the next element, which is spring. So this is the symbol for a spring, and we have marked K over here. K is the stiffness of the spring. K is the stiffness. So one end of the spring is fixed, and on the other end we are applying a force F, and due to the applied force there is a displacement of x for the element. Here the opposing force is represented as F suffix small k, and that is directly proportional to the displacement. So once again, remember, for mass the opposing force was directly proportional to the second derivative of displacement, and in dashboard the opposing force was directly proportional to the first derivative of the displacement, and in spring the opposing force is directly proportional to the displacement itself. So here the proportionality constant is replaced with the stiffness of the spring, that is K. So the opposing force Fk is equal to the stiffness of the spring K into the displacement X. Next, D'Alembert's principle. Sum of applied force is equal to sum of opposing forces. And another case in the spring, where the two ends of the spring are free, and we are applying a force on this side. So there will be two displacements applicable to the spring element. Displacement x1 over here and x2 over this end. So here the opposing force Fk will be directly proportional to the stiffness K into x1 minus x2. Okay. So these are the basic elements involved in a mechanical system, and you have to remember the basic expressions that we need to solve the problems. Fine.